Okay, let's get into it. Today's lesson is on thermochemistry. We talked about in our intro to heat and energy lesson that thermochemistry is the study of energy changes in chemical reactions. Well, that is good. We are doing chemistry where we are studying chemical reactions. So thermochemistry is actually a pretty complicated topic. And in a first year chemistry course, we're going to barely scratch the surface on some of these concepts because they tend to be a little bit on the confusing side. Also, some of the terms like enthalpy tend to freak us all out because that sounds kind of scary. So we're going to baby steps into this, and in my opinion, we're going to do mostly just the fun stuff on thermochemistry. So we will have our notes handout today. We're also going to need a calculator today because there's some math stuff that's required in our thermochemistry lesson, and specifically there's some stoichiometry in thermochemistry. So I'm super excited about this lesson today. This is my jam. Let's go. So thermochemistry. Thermochemistry is the study of energy or heat changes that accompany chemical reactions. Some reactions release heat and energy and some absorb it. And that, y'all, is why some reactions feel hot and some feel cold. So what I have here is a picture of the setup for the gummy bear explosion demo. What we did is we took a sample of potassium chlorate and we added, you guys, heat to it to decompose that potassium chlorate into potassium chloride and the oxygen. And we know that that oxygen was a combustion reactant that reacted with the sugar in the gummy bear and created that aggressive gummy bear explosion reaction. But I needed to have heat put into this in order for that decomposition to occur. So this is an example of a chemical reaction that requires some input from heat, right? Some chemical reactions absorb heat, like this specific reaction here, and some will release heat energy from the reaction. Okay, this brings us to our first scary term. It's okay, we've got this. Enthalpy. The symbol for enthalpy is H. So whenever you see H, we're talking about enthalpy. I just think about enthalpy as energy. Technically, it's a measurement of the amount of energy content in a substance. That's a fancy way of saying how much energy does this thing have, okay? The units for enthalpy are kilojoules, which this is a metric increment of joules, which we have seen as a unit for energy before. I can also express enthalpy in just plain old joules, but we tend to be using very, very large numbers for enthalpy, so a kilojoule unit probably is more appropriate, so I'm not having to write like lots of zeros and stuff like that. But that's a unit of energy. Well, that's great because that's what enthalpy really is. It's energy. Okay. Now I can expand this concept on enthalpy to this equation. I call this the Big Papa equation. If you get anything from this entire unit, I want you to know that the delta H of the reaction is equal to the H of the products minus the H of the reactants. Okay. That means that this is how you calculate something that is called the enthalpy of the reaction, or the delta H of the reaction. So the enthalpy of reaction is a measurement of the change in enthalpy in a chemical reaction. It's a measurement of how the energy content from my reactants to my products changes throughout that reaction, okay? And that little triangle, that delta symbol, means change in science. So the way that I get that is I take the difference between the enthalpy of the products at the end of the reaction and the reactants that are present at the start. As a result, then, we can calculate the energy that is either overall released or absorbed in a chemical reaction, okay? Big Papa equation, delta H is products minus reactants, products minus reactants. And the way I remember who minus who is P comes before R in the alphabet. So you guys, we are alphabetical here, which is super exciting. Products minus reactants. Okay. So now we're getting into the slides. You were like, what is she talking about when she says slide? I will explain this here in a second. But I can visualize an endothermic and an exothermic reaction by looking at something that's called a potential energy diagram. So these potential energy diagrams are used to visualize this change in enthalpy from my reactants to my products during the progression of the reaction. Okay, and we're going to dive into these slides a little bit more in depth when I focus on each one of these two types. But here I'm looking at for the first time these terms, endothermic and exothermic. What is she doing with this? The takeaway here is that if your delta H is a positive number, that lets me know that energy is absorbed in that reaction. And that reaction is endothermic. If your delta H that you would calculate from a Big Papa equation is a negative, that lets me know that energy is released in that reaction. And that reaction would be known as exothermic. Okay, so positive, absorb, endo. Negative, release, exo. Okay, so let's just unpack this a little bit further. We're going to start on my endothermic reaction, where heat is absorbed by the system. Now, if I'm going to be absorbing stuff into my system, and I'm a chemical reaction, okay, pretend I'm a chemical reaction, I'm absorbing that heat energy into my system, I've got to pull that heat energy from what is called the surroundings. So the surroundings are going to get comparably colder. So this is why these reactions feel cold. Because it doesn't make sense in my dumb brain to be like, well, if I'm absorbing heat, why don't I feel hot? Well, what I'm experiencing when I'm holding onto the beaker that has an endothermic reaction occurring into it is I'm holding and experiencing the surroundings, okay? So all that heat energy being absorbed means the surroundings feel cold. Okay, the reactions have a positive delta H because the products have a higher energy than the reactants. On the next slide, we're going to talk about this potential energy diagram and how I can calculate that it would give me a positive delta H. The main thing here on this slide, I want us to know endo. I think about an endo going in, so they absorb that heat energy, meaning the surroundings will feel cold comparably. Okay, so now let's dive into these potential energy diagrams. What is going on here? So this tracks, if I look on my x-axis, the reaction pathway. That just means as the reaction is occurring. Well, we know what starts a reaction is the reactant, so it's no wonder that the reactants are here at first, at the beginning of the reaction. And then I notice this thing. We go up a little bit. We hit this thing called an activated complex, and we go down a little bit, and then eventually we turn into the products, okay? This vertical movement of up and down is measuring the potential energy or the energy content, the enthalpy of those reactants and products, all of the players in this chemical reaction, okay? So I can calculate delta H. Delta H, by definition, is products minus reactants. Well, where's my products? Right here. If I draw a dotted line, I'm like, oh, well, that's the potential energy of my products, right? And in fact, if I draw a line, that distance from the very, very, very bottom where the potential energy would be 0 to whatever the energy is of the products, that is a way to measure the enthalpy of those products. Okay, so that's my energy of my products, right? Now, we take products minus reactants. Well, where's the energy of my reactants? Oh, they're right here. So what I would read on the y-axis for potential energy would be that energy of my reactants, right? Okay, now let's visualize this. If it's always products minus reactants, according to this endothermic reaction potential energy diagram, my products are a higher energy than my reactants. So I have a bigger energy and a smaller energy. A big number minus a small number is going to give me a positive overall change in reaction. Yes, because my products are higher energy than the reactants. So the products minus reactants will give me a positive delta H. Okay, so why is the slopey slope up and why is the slopey down? What is going on here? Okay, well, every single chemical reaction, no matter if it's endothermic, which endothermic absorb, or if it's exothermic, which exothermic releases, every single chemical reaction does involve an initial absorption of energy and a final release of energy in some way, okay? All reactions, I gotta take some energy in to get me to the point of an activated complex where all of the magic can happen and boom, 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 I am ready to create new products, okay? So this energy absorbed is going up and this energy released is going down or releasing that potential energy. Okay, now in my dumb brain, I'm like, oh my gosh, this is so many sciencey terms. I think about these potential energy diagrams as like a slide on a playground, okay? We all know if we're going up and down a slide, we first got to climb a ladder and then we get to the top and then we slide down, right? Well, this is a slide, you guys. Here, I have my first slopety slope as my ladder to get to the top of my activated complex. And then I slide down to get to the products at the bottom. When I think endothermic reaction, I think boring slide. And the reason why I think boring slide is because, guys, this would not be a very enjoyable slide experience for me, because the amount of effort that I had to take climbing up that ladder, it took a lot of energy to get up that ladder. That energy absorption was really great, right? All of that energy I had to absorb to get up to the top. Woo! Oh, that was it. That slide does it. That was not a lot of fun for me to slide down, and haha, laughter and giggles, releasing energy on my slide down. So overall, even though there is an absorption and a release, I had to absorb more energy than was released at the end. So I have an overall absorption in these endothermic reactions. Okay, these are the boring slides. It is not fun. It was not enough fun had by the amount of effort required to get up that slide. Endothermic reactions are your boring slides. Okay, now we're chemists and we like to write things called chemical equations. I can use thermochemical equations to show what heat transfer is going on in a type of reaction. So for endothermic reactions, they will have heat as a reactant. Okay, so a general skeleton term is I will have my reactants listed, and then heat, and then a yield sign, and then my products. Now, I'm not going to put the word heat usually in a reaction. Usually I like to put a number. You're like, what is going on with that number? Well, I see 198 and I see kilojoules. We know that enthalpy, or heat energy, is measured in kilojoules when it comes to thermochemical reactions, right? I'm also seeing that number on the reactant side. That lets me know that that sulfur trioxide, in order for it to decompose into sulfur dioxide in water, it's going to need some energy input or an absorption of heat to get that decomposition to happen. I see that and I know that. I know this is an endothermic reaction because I see it on the reactant side. That means heat is absorbed for that reaction to occur. Now, I can also represent a thermochemical equation this way, okay? I can just write the normal decomposition reaction as is without any heat stuff within that equation. But then off to the side, I can tell you what the delta H is. I can say, hey, delta H for this reaction is a 198 kilojoules. Noticing that delta H is positive. It does not have a negative 198. So that lets me know that that reaction will require 198 kilojoules of energy to be absorbed for that reaction to occur. So here we go. Thinking here is endo means absorb, means that I have a boring slide, right? And my delta H is going to be positive. So remember that endo means absorb. I see N-E-N, and that makes me think coming in. And I do a lot of hand motions this unit because myself needs to experience things like going down slides and visualizing these transfers of energy in these reactions. Okay, so that was my endothermic reactions. Let's talk about exo. They are the opposite in every single way. So for exothermic reactions, heat is released by the chemical system to the surroundings. And we talked about last time, when I'm feeling something, I'm feeling the immediate surroundings of that chemical reaction. So as a result, these exothermic reactions will feel hot. Okay, these reactions also have a what? Negative delta H. And the reason behind this is because, unlike my endothermic slide, I am seeing something a little bit different. My products have lower energy than my reactants did to begin with. Okay, so let's dive a little bit more into that. So we said that as a negative delta H. I get a negative delta H from these exothermic reactions when I take products minus reactants. Let's visualize this. So here is my potential energy diagram. I can see here's the energy of my products. Oh, my products are very low energy, right? And my energy of my reactants are over here. Oh, they really high energy. Well, the difference between the energies of the products and the reactants, y'all, that is where we get that delta H value. But when I subtract a small number, I take a small number in my products and I subtract from it a comparatively larger number in my reactants, a small number minus a larger number, I am going to get a negative number. And so that lets me know I have an exothermic reaction, that I would get that negative because the products are lower energy than the reactants. Okay, now let's go back to my slides. We like my slides. We said that all potential energy diagrams, no matter if you're exothermic or endothermic, you're going to have some sort of a slope up and some sort of a slope down. No matter where you start or where you end, that's going to determine whether you're endo or exo. But looking here, my exothermic reaction is the exciting slide. We talked about the slopey slope up is the energy absorbed to get to the magical state of the activated complex where the chemistry is allowed to occur, but that requires effort and absorption to get up that ladder. That's the not fun part, right? But the slopey slope down is me sliding down the slide. I'm super excited. That experience is wonderful. I'm laughing, I'm giggling. That energy is being released with joy from my body. So these exothermic reactions, I have more energy released at the end than was required to be absorbed at the very beginning. As a result, these exothermic reactions are net in energy released. So exothermic reactions are the exciting slide. The endothermic reactions are the boring slide. Like, come on, that ladder is way too long, and I'm too old for these long ladders. Okay, just like with my endothermic reactions, I can also take my exothermic reactions and display them as a thermochemical equation with some information. My exothermic reactions have heat as a product, okay? So looking at this, I will see my reactants, my yield sign, and my products, and my heat will be on the product side. So here's an example. I have sulfur and oxygen in a synthesis reaction coming together to make sulfur dioxide. Ooh, I see 594 kilojoules there at the end as a product. That lets me know that heat was released from that synthesis reaction to make sulfur dioxide. Another way I can show it is I can not have that number in my chemical equation, but I can have like off to the side. Well, here's the delta H for this reaction, by the way. Noticing something really important. The delta H of the reaction is negative 594 kilojoules. So if I'm just stating what the delta H of the reaction is, I have got to represent it as either positive or negative, okay? Because that lets me know what side of my reaction I'm going to be on, right? If it's here embedded in the equation, if I see it on the product side, I'm like, yeah, that's exothermic. That is heat released. But this is how they let you know which side that heat is required to be a part of. So I think exo is heat exit, which is super exciting. Okay, let's talk a little bit more like in detail about the little slopey slope up and the slidey slide down. Yes, I know it's a ladder and a slide, and that's how I remember it, but there's really something chemistry going on here. But for both endothermic and exothermic reactions, that slopey slope up represents the breaking of the bonds in my reactants. And that process of breaking bonds, since that is represented by the slopey slope up, that's an endothermic process where energy is absorbed, right? Now, the forming of new bonds to make the products, that's the slopey slope down. That's actually an exothermic process where energy is being released. And sometimes kids get this a little bit backwards. They're like, I thought the breaking of bonds is like releasing energy because that's what my biology teacher told me with the ATP of it all. Now, your biology teacher's not telling you the full story about actually what is going on to make the ATP, you guys. But if I think about it this way, if I were to try to break a pencil, it is just not going to spontaneously break on its own and like shoot energy at my face. It is not an exothermic process. I have to put in energy to try to snap that pencil in half, and that's me making an endothermic process happen. That energy has to be absorbed into the pencil, same way as that energy needs to be absorbed into my chemical bonds in order for them to break. So the slopey slope up means breaking the bonds to get to that activated complex where all of the atoms are like, we are ready now to do our magic, and then bonds are snapping together and forming, and that part is the exothermic part of the reaction. So once again, I don't care what type of reaction you are. First of all, what type of reaction? An endothermic or exothermic? Is it a exciting slide or the boring slide? Well, it looks not fun to me. It looks pretty boring because that slide part is not very long, right? So this is an endothermic reaction. But the endothermic part, that slopey slope up, is the breaking of my bonds in my reactants. And the slopey slope down is the forming of the new bonds in my products. The endothermic absorb and the exothermic release. Excellent. Okay, now I want to talk about what's going on with this activated complex up here at the top here of all of my slides. This brings us to the conversation of activation energy. And you will usually see activation energy symbolized by a capital E with a little sub A. Okay, the activation energy is the minimum energy required for a chemical reaction to occur. Now, this top part, the top of the slide, all chemical reactions have to get there or else they cannot slide down and create products, okay? And we know getting up there requires an energy absorption. If I am not given that amount of energy, I cannot make it up the ladder, which means I cannot fall down the slide, which means no chemical reaction can occur, okay? So that's the minimum amount of energy required for that chemical reaction. Now, there's something real fun called catalyst. A catalyst is anything that can speed up a reaction, and it does that by lowering that activation energy. Okay, so literally what a catalyst would do is he's like, I'm gonna take that slide a little bit lower here to where it makes that ladder much less steep, to where less energy is required to now get that chemical reaction started. So that's what catalysts do. They just lower that activation energy. So when I think activation energy, I'm like, oh my gosh, how am I supposed to remember all these parts of the slide? Activation energy is just the ladder, you guys, okay? It is the difference between the reactants, meaning the ground, before you even scale the ladder, and the activated complex, means the top of the slide. That is the ladder, you guys. In an endothermic reaction, it looks like that activation energy, or the distance from the reactants to the top of the slide, is pretty large, right? Versus in an exothermic reaction with a little short ladder, the exciting slide, right? That distance is not very big at all, right? But both of them, no matter what type of reaction, when I'm measuring activation energy, it's the energy difference between your reactants and the top, the activated complex. So now we have a real fun summary video on just kind of summarizing the difference between these exciting slides of my exothermic reaction and my boring slides of my endothermic reactions.
Some chemical reactions like this one gives off heat. Others, like photosynthesis, absorb heat. Welcome to Moo Moo Math and Science in exothermic and endothermic reactions. A chemical reaction in which energy is released is called an exothermic reaction. Exo means exit, and thermo meaning heat or energy. An exothermic reaction can give off energy in several forms, including heat and light. The energy released in an exothermic reaction is sometimes written as a product in a chemical equation. Take a look. An exochemical reaction can also be thought of as a downhill reaction because the products have less energy than the reactants. As a result, energy is released. An endothermic reaction is a reaction in which energy is taken in. Endo means to go in. The energy that is taken in during an endothermic reaction is sometimes written as a reactant in the chemical reaction. An example of an endothermic reaction is an ice pack. When you mix the pack, the chemicals mix and heat is absorbed and the pack gets cold to the touch. An endothermic reaction can be thought of as an uphill reaction because the reactants have less energy than the product. Reactants need heat or energy for the reaction to occur from the surrounding.
Okay, so let's dive a little bit more into depth about looking at maybe some of these potential energy diagrams together. So I'm actually going to bounce down here to our document camera, and we have this little handout that gives us some pictures of our potential energy diagrams for an exothermic reaction and an endothermic reaction. And then it has us do some math here with me giving you some examples of the potential energy of your reactants and products. Before we get down to those, I thought we would just kind of maybe recap on these graphs what we got going on here. Here's our big papa equation, right? The delta H of the reaction is equal to the products minus the reactants. I cannot stress enough how important this is. It takes you 2 seconds to write what equation you are writing. I will not make you have to write that whole thing. This sounds good to me. Products minus reactants, products minus reactants. So if I'm looking at my exothermic slide, remember exo means release, right? And exo also means a negative delta H. So those three things should always just be as one thing in your brain, okay? So technically, in order to get that negative delta H, my products minus reactants is going to be a negative number, right? So here's my energy of my products. So that's my H of my products. And here's my energy of my reactants. Oh my goodness, that's too much lead. Okay. Here's my energy of my reactants, or my H of my R, okay? The products minus the reactants, this is a smaller number than this one is, so I am going to get a negative delta H, okay? As you can see here that I've diagrammed here, that the delta H is the difference in energy between the products and the reactants, okay? So this is a negative delta H if we want to add the negative in there. So that's my exothermic. Let's talk about endothermic. Endo is absorb. Remember coming in. And it's going to be a positive delta H, because by definition, if your delta H is products minus reactants, well, looking here, my products are my higher energy, right, than my reactants. So if it's products minus reactants, here I have a bigger number minus a smaller number. That's how you get a positive delta H. Once again, my delta H is the distance or the energy difference between my reactants and my products. And it is a positive on this. Amazing. So now let's do some math with our Big Papi equation down here. So it says for each of the following, calculate the enthalpy of the reaction, or the delta H, and then determine if the reaction is endothermic or exothermic. Okay, so what I've done here is I've given you the potential energy of the reactants and the potential energy of the products. It says calculate the enthalpy. Well, I know the equation for delta H. You immediately write it down. Anytime they say calculate the enthalpy, you're going to write products minus reactants, right? Okay, let's see. Do we have the energy of the products? We do. It is 1,578 kilojoules. Do we have the energy of the reactants? It is 2,514 kilojoules. We are going to write that in our substitution. So we have 1,578. Notice how I'm putting units of kilojoules in here. Minus, and then my energy for my reactants is 2,514 kilojoules. Okay, I'll get my calculator. I'm real excited. Am I going to get a positive or a negative? That's what's going to tell me if I'm endothermic or exo. I'm excited. Okay, 1,578 minus 2,514. Okay. Oh my goodness, look at this. I get a negative 936. I get a negative 936. So delta H is equal to negative 936 kilojoules. I see that negative. Negative is exo. Okay, that means that that graph, or that potential energy diagram, would look like the exciting slide, because I noticed that my products are lower energy than my reactants, which means the slide down is going to be much, much longer than the initial ladder up. So that's the exciting slide. Okay, let's do this one over here. So, calculate the delta H. Great, I know how to calculate delta H. Delta H is equal to products minus reactants. Great, I have the energy of the products. I have the energy of the reactants. We are ready to plug in. My products energy is 3,241 kilojoules. And my products, or my reactants energy, is 1,244 kilojoules. I can math that up. Am I going to get a positive or a negative? Let's see. Let's see. So we get 3,241 minus 1,244. Boom. That's a positive number. I'm like, oh my gosh, that is super exciting. So delta H is equal to a positive 1,997, and the units for that are kilojoules. It is positive. I have a positive delta H, so that means I have an endothermic reaction. And the reason why this is an endothermic reaction are the really boring slide with my reactants having a lower energy than my products. So that way my products minus my reactants does give me a positive number. So this is translating our information on our slides, our little visual diagrams, and showing that you can use the information from those diagrams to actually calculate the delta H of a reaction. Okay, so now we're going to bounce back up to the lesson. Okay, On level kiddos, you guys can take a back seat. You guys are not doing this concept of standard enthalpy of formation. I will let you know when we can come back in, but this is strictly for my honors kids. We're going to learn about the standard enthalpy of formation. You were like, there's a lot more symbols going on around this H value, okay? I've got a little subscript F. I got a little 0 up there. What is going on? This symbol stands for the standard enthalpy of formation, okay? And it is a measurement of change. That makes sense because the delta means change in enthalpy required to make 1 mole of any substance under standard conditions. Standard conditions just basically means like not like outer space conditions or like under the deep sea with a lot of pressure, just normal atmospheric pressures and temperature. Okay, but this is the energy required to make 1 mole of anything. Okay, so here are some examples of showing the process of making 1 mole of these things. Here I have made 1 mole of nitrogen dioxide. Here I've shown the process of making 1 mole of calcium oxide. Here I have shown the process of making 1 mole of carbon tetrabromide, okay? There's only one of those because there is no subscript in front of those substances, okay? Now, to make that guy, I did something here. I formed it from its single element components. Now, I know this is wackadoo. You're like, Sabaka, you told us we could not have a fraction for a thing. Yes, we're not going to write our own standard enthalpy of formation equations. I wanted to show you what an equation looks like for an enthalpy of formation. But regardless, every single time I make 1 mole of anything, there's going to be an energy process or an energy change associated with that process, okay? So the formation of 1 mole of nitrogen, or nitrogen dioxide, is going to be a positive 33.18 kilojoules per mole. That's actually an endothermic process because it's positive. The formation of 1 mole of calcium oxide, oh, this is exothermic. It's going to involve negative 634.9 kilojoules, or it's going to release that many kilojoules of heat. And this guy is 29.4 kilojoules. That's an endothermic process. But each one of these values are standard enthalpy of formation values for the specific substance that is formed from that process. You're like, where is she going with this? Okay, so here's a chart down here, and this shows some possible standard enthalpy of formation values for making water, making a mole of water vapor, making a mole of CH3OH, making a mole of this. So they're all a little bit different, okay? So here's something interesting. I can give you a chemical equation with some reactants and some products, and I can give you values for the formations of each one of these individual things. And I can implement my big Papa equation. Even though he looks a little bit more squirrely, it's okay, don't get freaked out. So from this table of given standard enthalpy of formation values, I can calculate the delta H of the reaction by taking the sum of all of my products minus the sum of all of my reactants values from the chart, okay? Y'all are like, oh my gosh, this is a lot going on here. Yes, I like to abbreviate this because there's lots of bubbles and subscripts and things, is I just write the sum value with the P minus the sum value of the R. That makes a lot of sense to me. This symbol means the sum, which means you take the sum of all of the products together, and then you subtract from that the sum of all of my reactants together. Okay, so let's kind of look at an example of what this is about first, and then we're going to practice one together. Okay, so here I have my chemical reaction equation. I've used some colors to help us out, okay? I have a combustion reaction here, and this is methanol, by the way. So methanol is going to combust, which means he reacts with oxygen to produce carbon dioxide and water. It is nice and balanced. I love that, okay? But by definition, and this is where the squirreliness happens, to calculate the delta H of the reaction, it's not the reactants minus products. It's actually color flopped, my products minus reactants, okay? So translating down here, I've got it in my shorthand form, the sum of my products minus the sum of my reactants. Well, who are my products? Looks like I've got carbon dioxide and I've got oxygen. Can I find carbon dioxide gas down here on my enthalpy of formation tables? Yes, he's right there. Can I find water gas down here on my enthalpy of formation tables? Yes, he's right there. Cool. Those are the enthalpies of my products. I got to take the sum of them. The only sneaky thing here, though, is that those coefficients make a difference. Those coefficients we know are like the mole ratio. That lets me know that for every 2 moles of carbon dioxide, I have 4 moles of water, right? So when it comes to the math part, not only do I pick out that standard enthalpy of formation value from my carbon dioxide, I've got to multiply it by the coefficient of 2, okay? And then to that, I add the 4 of the water molecules, right? And then I get to my reactants. You're like, great, reactants. Minus all my reactants. We love this. Great. We know that there are 2 moles of my methanol, and we grab our methanol value there, and we're like, all right, great. We are ready now to add together to that the oxygen. Oxygen is next. There is no oxygen. There is no oxygen in this table. Well, guys, y'all, by definition, a standard enthalpy of formation is the energy required to make 1 mole of a substance. To make. Oxygen, I do not make. He is an element, right? Yes, he is diatomic, but I have not created a compound between more than 1 element on the periodic table. Have I? No, I have not. Which brings me to, if you get a chemical equation and you are asked to do this process, if one of your reactants and products is just a single element, you get a 0, okay? So the delta H of formation of any single element that is not in a compound is always a 0. Okay, so let's do a practice one together. We'll bounce on down here. And, oh, yes, good stuff. Okay, so we already took all these notes. We already said that this is always going to be 0. I have an example problem. It says calculate the delta H of the reaction for the following using the standard enthalpy of formation values below. So over here, I've given you the standard enthalpy of formations for ammonia gas, for nitrogen monoxide gas, and for water gas. Cool, amazing. All right, I have a chemical equation. I'm ready to go. What thing am I using? I am using delta H equals the sum of my products minus the sum of my reactants. Okay, so I focus on my products first, okay? So here we go. We're going to expand this out because these problems take like a lot of space, and I am super sorry. It's going to be fine. We are all doing the same amount of work. The way I'm going to handle this is I'm going to put all of my products math work in brackets. That way I don't get confused, right? And then I'm going to do the subtraction, and then I'm going to put all of my reactants work in brackets. Okay, so we're going to tackle our products. We're going to open up a brackets. Who is my first product I want to handle? It's nitrogen monoxide. Well, how many moles of nitrogen monoxide do I have? I have 4. So I have to start off saying 4 moles of NO. Well, what am I going to multiply that 4 by? There's his enthalpy value. So we're going to say times 90.3, and this has got units of kilojoules per mole, okay? And the reason why the units are kilojoules per mole is that that's how much energy is required for every 1 mole of nitrogen monoxide, which is why I have 4. So if I multiply these two things together, the moles cancel out. My final answer from just these products will be kilojoules, okay? So that was, you're like, what is going on? But I just wanted to explain the units and why they're actually important to write in here. So that's my first product. My second product, which I'm going to add to whatever this value is going to be for me, is my 6 moles of water. And I'm going to actually specify gas. I probably should have wrote gas underneath here too. And you're like, why? There's only 1 water. Sometimes I'll give you a table with multiple waters of different states. And yes, they do have different enthalpy of formation values depending on what state of matter I am. So I got to make sure I pick out the gaseous water one, okay? So the water guy here is negative 46.1 kilojoules per mole, right? Okay. And then I'm going to bracket it off. That's all my products, you guys. Look how much work that had to take for me. I'm sorry. It's fine. We can do this. So all of those products, and I'm going to say minus, so I'm going to have to drop down here, and then I'm going to tackle all of my reactants. I got 4 moles of ammonia and gas, right? Well, my ammonia here is negative 46.1. kilojoules per mole, right? And then my second reactant, so I'm getting ready to blast him in here, is oxygen. You do not see oxygen on this list. Why? Because he is a single element that is not in a compound, which means his standard enthalpy of formation value is a 0. But I still got to show the math work for him. So I have 5 moles of O2 times 0 kilojoules per mole. Okay, so this is a lot of math work for me. Okay, I get my calculator out, right? So what I like to do is I like to open up my parentheses for my products, and then I moles times the energy plus moles times the energy, right? Close parentheses, and then minus, open up my parentheses for my reactants, the moles times the energy for the first reactant plus the moles times the energy for the second reactant in close parentheses. You're like, she's doing way too much explaining. I just wanted to tell you what I'm planning on doing here. So I go open. My first number is 4 times 90.3 plus 6 times negative 46.1. Close parentheses. So those are all my products, right? This is the first product and this is the second product, which I'm adding together. Your calculator does know order of operations. Minus, here's my reactants. I have a open parentheses. 4 times negative 46.1. And then my next reactant is the oxygen. I don't have to type in this because it's going to be a 0 anyway, but let's just for funsies type in 5 times 0. Yes? So here's my reactants, my first reactant and my second reactant that I'm adding together. But I've taken my products minus all my reactants, and let's see what we get. Okay, amazing. Okay, so I've gotten my delta H for this reaction to be 269. Let's check our rounding. You're like, oh gosh, the sig figs it all. What we have done here, guys, is a lot of adding and subtracting. The adding and subtracting rule for rounding is I'm looking at place value. Whichever number in here had the smallest place value or the least precise place value is what I have to round everybody to. And some of y'all are looking like, oh, but these moles are in the ones place. Moles is just a ratio, okay? Those are infinitely significant. It's not what we're looking for our rounding, okay? We're looking at like values that they have given us, measured values, which conveniently enough, they all have the same place, right? So all have hundredths place. So that means my answer needs to have a value in the hundredths place. Well, the calculator did not give me one. It's exactly 269. Great. So give me something there, a 0. Okay. Now, what are the units? You're like, I do not know. What are the units? Well, we kind of mentioned up in here that moles times a kilojoules per mole would only give me a kilojoules. So my units are kilojoules. I'm sorry about all the units work. That's extremely annoying, but guys, it's not that much of a different topic. It's just an extension of a topic because this is still all just P minus R. Delta H is equal to the products minus reactants. Now just the sum of all the individual values of the products minus the sum of all the individual values of the reactants. Okay, so that was super duper fun. Okay, now this is where everybody comes back in. Everybody has done stoichiometry before, so on-level kids, y'all are listening now. It says, using the enthalpy of a reaction in stoichiometry. You're like, oh my gosh, you guys. A thermochemical equation is any balanced chemical equation that includes the enthalpy change of a reaction with units of kilojoules per mole. That per mole part allows for us to use that enthalpy number value as how much heat is either lost or absorbed per mole of the reaction. You're like, what is she talking about? What mole of the reaction? So here's an example of a combustion reaction, okay? So this is one reaction, yes? One reaction is 1 mole of the reaction, okay? So for every one of these that I run through, it's going to release, I'm saying release because it's a negative, 1,790 kilojoules, okay? If I did 2 of these reactions, it would release double that. For every one reaction as it is balanced, that is the value, that enthalpy of reaction value. That's why it's kilojoules per mole, technically. Here is water changing phase from a liquid to a gas. This process here is a positive number, which means it's endothermic. But for every one of these processes, or every 1 mole of this process, it will absorb 44.01 kilojoules. So what does this mean in terms of stoichiometry? That split unit means a lot. Whenever I have something that is a split unit, I can use that as a conversion factor. Whatever that numerical value for the delta H is, that tells me however many kilojoules are in every 1 mole of the reaction, okay? So for that first example on the previous slide where I had the negative 1,790 kilojoules per mole, I can take that and put that into some stoichiometry and say that, hey, that's negative 1,790 kilojoules per every 1 mole of the reaction. Or I can flippity-floppity. Same thing with the other examples, conversion factors. Okay, so let's do some practice problems on some stoichiometry, and this will be the last thing that we do today. which, oh my gosh, this was a very complicated lesson. It is. And like I said, it's only scratching the surface of this thermochemistry stuff. So what we just talked about is this being very, very important. This is what I can turn my delta H value into and then plop it into stoichiometry. All right, so you're like, oh, stoichiometry. Stoichiometry, it always has to start with a chemical equation and a balanced chemical equation, because no matter what type or flavor of stoic we're doing, we are going to be using the coefficients as the mole ratio in some way. But they've given me the chemical reaction. Are we balanced? We are balanced. How nice am I to do that for you guys today? Okay, how many kilojoules of heat are either absorbed or released when moles are burned according to the following equation? Oh my gosh, what is going on? We have been trained to find our number in our problem and circle it. I am starting you off with 0.75 moles of magnesium. We're going to write that information underneath magnesium, yes? So 0.75 moles. Cool. So where are we trying to take this to? How many who? Kilojoules of heat. Kilojoules of heat of who? Kilojoules of heat for just the reaction. So this is something a little bit sneaky about thermochemical stoichiometry. So I'm not necessarily going to anybody. I'm going to just tell me what the energy value is if I were to start off with that many moles of that magnesium. You're like, okay, where is she going here? So we're ending up here is where we are ending up. You're like, okay, this is blah, blah, blah. What I want us to notice is we haven't even looked at this here. I've given you the delta H of the reaction. I'm like, hey, that is that. So this is actually what I'm going to be using as my conversion factor. Remember looking at that? I get to implement that as negative 1,204 kilojoules per every 1 mole of the reaction when I need to get to that step. You're like, what is she doing? Okay, it's fine. We can start with our given. I should probably do less talking. I feel like a lot of this is better explained once I start actually doing the process. But I write my given. That's nothing new. And my given is of magnesium. And we're at moles. We've been trained that when you get to moles of your given, you are ready for a mole ratio time. You're like, great, magnesium has that too. That is what I'm going to be using. Yeah, that's what you're going to be using. You're for sure going to be using that 2 moles of magnesium on the bottom, right? You're like, okay, but she said I'm not going anywhere. So what goes on the top? Well, the mole ratio here is going to be between the moles of magnesium and the moles of the entire reaction. This tells me there's 2 moles of magnesium in every 1 reaction. So 2 moles of magnesium in every 1 mole of the reaction. And I don't think I've mentioned before, RXN is the abbreviation for reaction. So I do that because now I cancel off. You're like, okay, now I'm just looking at what is the reaction going to do for me, not somebody specific within the reaction. So I'm like, well, I need to find how many kilojoules of heat energy are released or absorbed. Y'all, I can write this to convert from moles of the reaction to how many kilojoules of heat or energy are experienced in this chemical reaction, what change is experienced. So that means for every 1 mole of the reaction, I will release negative 1,204 kilojoules, okay? So what I've got going on here is I have turned this guy into a usable conversion factor for me, okay? So the result of this mathematically, because of my units canceling off, will give me an answer in kilojoules, which is great. That's what they wanted me to solve for. I feel so happy about that. So I get my calculator out. I go 0.75 times a negative 1,204 divided by 2. And I get a negative 451.5. You were like, great, what do I round to? How many sig figs are in your given number? That 0 is not significant. It is only 2 sig figs, which means I need 2 sig figs, which means my answer is going to be negative 450. Just do not put a decimal after that 0. Okay, that is 2 sig figs. What are the units? Kilojoules. Now here's something a little bit sneaky about thermochemistry is that the negative can be a little bit fuzzy. I could not say negative 450. I could also just say 450 kilojoules. But you better make sure if you are just leaving out that negative, you tag on the word released, okay? Because I need to specify if it is released or absorbed, including the negative, right? Lets me know that it's released. So you could also say 450 kilojoules released. But you must have the released part there, okay? So we'll write that there off to the side. Okay, I'm going to move on to the next one. We have 2 more to do, and then we will be done today because I'm already getting tired. Okay, it says how many grams of oxygen. Well, first of all, do I have a balanced chemical equation? I do. They're not super exciting. And wait a second. What is that? Who is he supposed to be in here? What is going on here? I have something that is a kilojoules. He is not a chemical formula. What is going on? I have just represented my delta H value inside of the equation. We went through this conversation in our notes. That's the delta H value. I just put it in there. Well, why'd you put it in there? What purpose does that serve? I'll tell you. Which side of the equation is that 213 kilojoules? It's on the reactant side. That means heat is needed to be absorbed to get the reaction started, right? So that means that this value is a positive 213. But this represents how many kilojoules are in every one of these. So I'm going to say per mole of that reaction. Cool. So that is important. We know we probably will be using this as a conversion factor like we did up here. Now let's get to the question. What am I starting with? What are we trying to get to? So they said, how many grams of oxygen gas will be produced if 535 kilojoules of heat is supplied to the following reaction? Okay, cool. I have 535 kilojoules of heat. Great. Who? Just of heat for the reaction. It's not anybody specific in the reaction. It's just for the reaction. You're like, oh my gosh. In fact, let's just go ahead and just write that and see how this can maybe help me figure out what to do next. 535 kilojoules, right? So we'll stop there, and I want to figure out where I'm trying to go to. How many grams? How many grams of, oxygen gas. That is somebody specific within my reaction. Oxygen gas is right here, so I'm going to go question mark grams. So I'm starting from a general energy absorption here from this reaction, and I'm like, well, how many grams of oxygen would be created with that amount of energy absorbed? Okay, great. Well, I see kilojoules. What am I doing here? What am I doing here? Look at that. That means I can put the positive, and you don't have to put positive. If it makes you feel better, you can put positive. I won't count off for that. 213 kilojoules per every 1 mole of the reaction. Boom, boom. So now I'm talking about one of these reactions. Well, how do I leave talking about the entire reaction to talking about just the oxygen part? Y'all, I implement the coefficients. For every 1 mole of the reaction, or for every 1 reaction, I have 3 moles of oxygen, or I have 3 oxygens. You see how this works? It's like a mole ratio, except just between somebody in the reaction and the entire reaction. Okay, so now I am just talking about oxygen, but I wanted you to give me the grams of oxygen. We have done this before. We were going moles to grams. We were just using the molar mass, right? Which states for every 1 mole of oxygen, I have 32 grams of oxygen. Yes? Looking at that. So all I've done here is I've just used my delta H value as a conversion factor. Yes? Okay. So now we are ready to the math part, which is super exciting. We have 535 times 3 times 32, and then I'm going to divide it by 213. Cool. That is my answer. How many sig figs? I have 3 sig figs here, which means I need 3 sig figs over here, which means I need 241. What are the units? It's the only thing I've not crossed off. So it is grams of oxygen. Awesome. Okay. So once again, I feel like I kind of want to do some circling to let you know what the new pieces of this specific stoichiometry that we have started with. Me taking that was actually in my chemical equation. Notice he was on the reactant side, being able to make a statement that I put in as a conversion factor. All right, last problem. Okay, last problem. It says when 15 well, first of all, where's my chemical reaction? Oh, it is there, and it is balanced. You're welcome. I've also given you the delta H value. Oh, I love that. I notice it's negative, which means it's exothermic. Okay, let's see now what they're asking me to do. When a 15.1 gram sample, they're giving me 15.1 grams of who? Ethyl alcohol. Well, I do not know the formula for ethyl alcohol. Well, let's see if we can figure this out by process of elimination. I know that is oxygen, and that is carbon dioxide, and that is water. So that's probably ethyl alcohol. It is. So I'm going to put 15.1 grams. If you want, you can get train track started because you know you were doing some stoic. 15.1 grams of C2H12 I did that thing where I didn't give myself a lot of room. That's okay. So I'm starting there. What am I trying to solve for? How much energy in joules is released as heat? Energy is not specific to anybody in here. Energy is specific to the entire reaction, which is why I have this guy that I'm going to have him help me here. But before I have him help me here, I need to get to the moles situation, right? Well, I started you off at grams. So my first step is to put grams of my ethyl alcohol down here, my C2H5OH. And that means my molar mass. So I'm going to grab my periodic table here in a second, right? And that's for every 1 mole of that C2H5OH. So this is my molar mass step. So on my periodic table, I have carbon who has molar mass of 12.01, and there are 2 of them, times 2. Plus I have hydrogen who has a molar mass of 1.01, and there's 5 right there. Plus oxygen's molar mass is 16. Plus I got an extra hydrogen on the end who is still a 1.01. So my molar mass for ethyl alcohol is 46.08 grams in every 1 mole. Amazing. And the grams of ethyl alcohol cancel out. I'm at moles. Moles, moles, moles. Mole ratio time. Except the ratio I'm using is not between ethyl alcohol and something else. It is between ethyl alcohol and its own reaction. There is a 1 there per every 1 reaction. So that means there is 1 mole of ethyl alcohol for every 1 mole of the reaction. Yes? Okay, now they wanted me to solve for the energy. Well, the energy, y'all, I can use this and figure out how many kilojoules of energy is either released or absorbed. So this now turns into, for every 1 mole of the reaction, there is a negative 1.37 times 10. Oh my gosh, my pencil is giving me problems today. Times 10 to the 3rd kilojoules. That negative lets me know it's exothermic, which means it's going to be a releasing process. Okay, so, and I did that because now moles of reaction are done. I know my answer I'm going to get is an energy unit of kilojoules. Okay, so I have 15.1 times negative, we can just write that as 1,370 because times 10 to the 3rd is that many places that way. If you want, you can write it in scientific notation or type it in scientific notation in your calculator. It is up to you. You can choose your own adventure. Okay, and then I'm going to divide that by 46.08, right? Okay, so that is my answer for this. How many sig figs? That's got 3 sig figs. My given has 3 sig figs, which means I need my answer rounded to 3 sig figs. So rounded to 3 sig figs, I have a negative 4, 4, and then my last number is going to be actually a 9. That 8 is going to be rounded up to a 9. Now the units for this are kilojoules. Okay? Now here's something sneaky and important. On level kids, this was your answer. I just had y'all take it to kilojoules. Honors kids, I had y'all take it to joules. Well, how am I going to go kilojoules to joules? King Henry died by drinking chocolate milk, which means you're going from the king, the kilo, to your base unit of a joules, which means you rock that decimal place 1, 2, 3 places that way, which means my answer in joules is negative 4, 4, 9, and then 3 zeros tagged on to the end on joules. Awesome. Okay, so what we've done here is we have now done some fun stoichiometry with our delta H of our reaction, right? We also now know that I can use a delta H of reaction, whether it's negative or positive, to tell me if it is an endothermic or an exothermic reaction. We also now know how to interpret a potential energy diagram, meaning those exciting slides are those boring slides. We know that delta H is products minus reactants. We've done a lot of fun stuff here, but H is not a scary term. Enthalpy is not a scary term. It just means energy. But we can manage or measure energy changes within a chemical reaction by studying these enthalpy values.